1357. Take it and study for the exam, right? Did everyone get the schedule on chapter 5, 3, 5, and 7? You? I think you probably get a. You sure you don't get it? I think you get it.
Oh, the last one.
Yeah. Chapter 7, chapter 5. You. Alright, so we are going to finish chapter 8 today. So then we will have the exam 2 Thursday, November 19th. Alright, so chapter 8 it will be the last chapter on the exam 2. And so in this chapter we study some of those patterns, the periodic patterns. One pattern is about the atomic size. When we talk about patterns, usually we'll talk about the pattern like in the same group or the same column goes up and down. And we also talk about in the same period going from left to the right or right to the left. Alright, so for this atomic size pattern, so both of these arrows will be our decrease direction. So you can use this pattern to predicting sometime. If I give you like a pair of atoms, or maybe I will give you a group of atoms. Sometimes you cannot decide. Simply use this pattern. Use these two patterns. Right, so let's do this example first, and then we'll do the CRE. Right, so for the first two elements is nitrogen and fluorine, N and F. So these two are in the same period, and N is number 7. So if you see this number 7, that's an atomic number. And then I think both of them in second period. So you start with boron on this side, the so-called P block, and then carbon, then nitrogen, then oxygen, then fluorine. Right. So all these few elements is in our so-called second period. So the atomic size is good pattern, right? Maybe like 1 or 2 numbers is not in like these two arrows or general arrows. So if I give some problems about the atomic size, you can say either you know or either you cannot decide. Like this one, obviously this N is on the left side, and the fluorine on the right side. So we know for those atoms on the same row or in the same period. So those atoms on the left side, those atoms on the left side is bigger. Right. So this N is a larger one compared with fluorine. Very simple. And so then next pair is about, so you circle like the nitrogen is bigger. And the next pair is the carbon and germanium. That's the carbon in this the so-called column. Column also called the group. So carbon on the top. And so carbon, the atomic number is 6. So this 7 and 6 are those so-called atomic number. All right, and then below carbon you have the silicon Si, and then below that you will have the germanium Gg. Right. So So you can see this arrow here goes up in the same column, the size decreases. So therefore, carbon is smaller and the germanium is bigger. So therefore, if we find out that very easy. Right? So the next one is about, let's see, about N and aluminum. So aluminum, let's say, is in the other period, is below the boron. So aluminum is right here. Aluminum right here. And so then you can, what you can see is you cannot simply use one like arrow to go to starting from like one atom, get to the other atom, unless you use the diagonal. Well, so if you use two arrows, the pattern like this. If you starting from either one with two atoms, let's say start from N. And I will take two steps because they are not in the same row or in the same column. So I will go like from let's say from N here, and I will go like one step like this, left and right. Then another step. So let's say another step. It will be this, right? So these two arrows, and if these two arrows were, these two arrows direction, pointing to the same pattern, and maybe pointing to increases or decreases, and then you can have a conclusion. So let's say we start from here. So we start. Where you start doesn't matter. You can start from AL, or you can start from N. And just figure out that you need two arrows, two steps. Right. So you start from N, you go to like this boron, right? So this arrow, let's say you go this direction. So this arrow, now this arrow tell you is what kind of arrow? Is decreases or increases? Increases, the size increases, right? Right. So you have increase arrow here, and if you get another increases arrow on the second arrow, then you can like recycling and you can predict. Right. So the other arrow, let's say the other arrow is here. That means we're starting from here, start from the boron, right, and go to AL. Right? And what kind of arrow is this arrow? You go from boron to AL. Is that increases or decreases? Okay, now, so this one, let me change this color back to the yellow thing. So this arrow, did not change. This arrow, as you said, worked. Increases, right? Now the other arrow, so this arrow, you said is also what? Also increases. But you have two arrows, both of them increases. That means you know right away. Okay, so that means AL is bigger. Because you start from N, increases one step, then you go to another step, increases again. So you see from N to AL, increases, and then you increase it again. Did I miss something? Right. Excuse me for that. Let me just. That's better now, right? Right. So therefore you just use these two basic patterns. Okay? Left to the right, right to the left in the same rule. Most of the time for those patterns. And then later on you will see you probably can even jump in between two rules, between two periods. So then the other pattern is up and down, and down and up and down. So if two patterns, you can draw the diagonal, but usually you will just use the two patterns. So like in this example, so we have one horizontal one, one vertical one, and if two arrows tell you the same direction, then we know the result. Right? Right. So now let me erase this and see the last one. Okay. So we figure out N is bigger, germanium is bigger, and AL is bigger. Okay. You compare AL with GE. Okay. So where are they? Let's say AL is here, then SI is here, and gallium GA is here, and then GE is here. So these are the two elements we have in this smaller area. Right. So again, you can just starting from either one. Okay? So now this time I will start with AL. I will start with AL, and I will draw one arrow like this. And then I have to go to GE, and I will draw another arrow from SI to GE. So then just be careful, see if you get two arrows tell you the same pattern. Okay? So the first arrow will tell you is decreases. The second arrow tell you it is increases. Got that? So if you have a two arrow, two step, and one step will tell you something getting smaller, and the other step will tell you something getting bigger, then obviously you don't know, you cannot tell precisely. Right. If you cannot tell precisely, that means you just say you cannot tell precisely. And so this is one pattern as I said in this chapter. Right, now do the CRE 8.8. So I give you I give you 5 items, and you want to put these 5 items. I just read the question carefully. Those are very, very easy questions, and the problem usually your usual mistake is you miss like what you want to, like what kind of order you have. Okay, increasing order, which means you starting from something small. Okay? You're starting from something small, getting something bigger. You said E. Let's see E. So we have these few items. And fluorine obviously is here in this corner. That we said you go this way getting smaller, going this way getting smaller. So therefore this corner here will be our smaller radius corner. So the atom's radius on this upper right corner is smaller. Right? So that's a good starting point. And then you can see that sulfur is to the left and down, so therefore this sulfur is a little bigger. And then Si even to the left, so even bigger. And then Mg even to the left, so even getting bigger. And then potassium similar, so go this way, have 2 directions, both 2 directions tell you is bigger. Yeah, so you are right, I think the answer is E. What do you think of this? So this similar, you want to put this 3 atoms and in the order of increasing atomic radius, which means you are going to starting from something smaller. Okay? And the atomic radius, the small one will be on the up and the right, right side corners. So fluorine, and so that's the smallest one. You said is A. Does that make sense? Yeah. Okay, so Cl is smaller. Cl is right here. and then phosphorus P on the left side getting bigger. Then BA, you like far to the left side. Right, so the answer for 8.9 is A. Right, so I think we are going to review briefly about the electron configuration again. So we already studied the electron configuration for the atoms, and so then we can use the electron configuration understanding some of those chart patterns, and even get those configuration for the charged atoms, which is the ions. Right. For example, we already seen that many metals and non-metal form one type of ion, and then that charge on that ion is unique, is predictable, and based on its position on the periodic table. Okay. So even though you cannot do that prediction for all those atoms or all those elements in the periodic table, but I think there's many we can see that pattern. So even though not for every atom, so that means it was a while for us to find out the reason of understanding. So that good pattern, like in one chart for like one element, and always that chart number is particularly the main group or the group A element. For example, group 1A, those alkali metals will produce 1 plus ions, cations, and group 2A will produce 2 plus cations. Group 7A on the other side of the periodic table will become non-metals, and they usually will not lose the electron that easy. On the opposite, they will try to receive some extra electron and become stable. So group 7A, fluorine, chlorine, bromine, and iodine, they will receive 1 extra electron and become 1 negative. Group 6A, and for example, oxygen, sulfur, and selenium receive 2 extra electrons, become 2 negative. Right. So we find out those atoms produce ion by either gain electron or loss electron, resulting in an electron configuration that is the same as the nearest noble gas. And that is one reason we do that, or give us like one theoretical background to understand. Right? So we studied that, I think, seems like very early chapters, and now we can see the reason. Right? And so then you can like also write out the electron configuration of the ions. And again, in this chapter, we usually talk about the ground state. Right. For the anions, which means they will have some extra electrons. So anions are usually formed when non-metal atom gain enough electron to have 8 valence electrons. So 8 valence, this 8 not really precise, and I think precise that you already see on the last slide the configuration of the noble gas. So whether they have 8 or like 2, and depend on what is their nearest noble gas. If they have 8, that means you will have this S completely filled. So S will be S2, and then P will be P6. As we know, the S subshell has only 1 orbital, and each one orbital can only have 2 electrons. And we also know the P subshell has 3 orbitals, and each orbital can have 2, so therefore maximum for the p subshell is 6, and then 2 plus 6 is 8. So that's is the so-called 8 rule, octet rule. For example, sulfur atom, the sulfur free atom, the neutral atom has 6 valence electrons. So we studied last week, and for those group A atoms, and the number of valence electrons is the same as the group number. So that's like the result. Right. So this 6 valence electron here, and so that obviously that's not same as the nearest normal gas. The nearest normal gas for sulfur will be argon. So therefore it can like react with some other atoms and gain like 2 more electrons and become a configuration like this. So I circle these last 2 subshells because this is the only 2 subshells that is the valence shell. The other electrons pretty much keep are the same. You compare this one with this one, the 3s is still the same. The only difference is the 3p4 becomes 3p6. And that tells us, so this sulfur gain like 2 extra electrons. And you obviously see the electron for the sulfur atom is 3p4, and here is 3p6. So 2 more electrons. And then therefore that become like an S2 negative. And also that tells us this configuration right now altogether is same as the configuration for argon. So this configuration is for argon has 18 electrons. Now we know argon is a noble gas. And then we know noble gas is stable. So that is they try to be like a noble gas, even though sometimes it's really difficult for them to be like a noble gas, and especially those transition metals. And once they getting like, if they can get into the configuration of noble gas, they become stable, very stable. Right, and so that's let me go back here like finish. So that means it's very easy to get the electron configuration for the anions. You just adding electrons, adding like enough electrons to the lowest available orbitals, depending on how many electrons you have. How many electrons you have depends on the charge. If you have 1 negative, you have 1 extra electron. If you have 2 negative, you have 2 extra electrons. So just keep what we did before. Even though there are some atoms not really all have the same pattern, and there are some exceptions, but for most of atoms, just adding like according to the 3s and 3d, 4s, 3d, and so on. Now the cation, you get the cation by taking electron away from the neutral atom. And then taking electron away actually is not that easy compared with adding electron on. Adding electron on just adding to the lowest available orbitals. Take electron away, and you have to say like which electron you want to take it away first. That again depends on like what kind of element we have. And maybe we will have those group A elements, maybe we will have those transition metals. Let's see, for the group A elements, we lost electron from the NP first, then from the NS. And so both of these 2 notations, and is the highest. So the highest Prince principal quantum number. Right. So that is easy, and if you have the electron configuration for the group of A metals, and you just take the electron away from the highest NS or the NP. For the transition metals, so that's little difference. You take the electron away from the NS first, and then from the N minus 1D. So keep that in mind. So what electron you take away first is very, very important. And why we have these two patterns? Why we have these two ways? And both of these two ways were like give us a result that has a new lower energy level valence shell. So this process, even though you are ending up with lower energy valence shells, but it's endothermical process. So for example, let's see like one example for the group of A elements, and I will see the transition metal from the next slide. Let's see you first need to know like what is the electron configuration for the neutral atom. For the magnesium atom, and we have 12 electrons, so therefore you will have this electron configuration, and this is 3s2 in our valence shell or the valence subshell. So according to our pattern, and you need to take from the NP first, then the NS. And in this example for magnesium, we don't have that NP. So our highest, the highest principal quantum number N in this configuration is 3. But so we only have a 3s and we don't have a 3p. If you have a 3p, so take the electron away from the 3p first for those group A metals. Right. So for the magnesium, you just take that 2 electron away from the 3s, and you take all the electron away. You have 2, just take both of them away. You take 1 electron away, you get 1 plus. You take 2 electron away, you get 2 plus. Alright, so you will end up with this configuration, and then because you take 2 electron away, so therefore you get a 2 plus, and then this becomes 0. If it's 0, you don't have to write 0.
About the sulfur, you say it's only sulfur 2 minus, but they also the sulfur 4 minus in the 5. So why is that happen?
That can happen, but not that stable. Not like the naturally. You can like produce some of those extreme situations. Maybe produce a vacuum, maybe some of those special situations, and you can put some extra electron on it, but probably that will not living for too long. It will like just collapse or doing something very quick. Any other questions? Okay, so why is always, for example, this statement tell you. So even though you ending up with like you take the electron away, your valence shell become a lower energy, but it's an endothermical process. That means the whole process take you from a lower energy place for a high energy place. You understand that is because even though this the valence shell, those shell which is empty now, has energy lower. You take the electron out of that shell, so electron become free. That free electron has a lot of energy. So where the energy for the free electron come from? It comes from the environment. You have to supply the energy to make the electron become free, get away from the atom. All right. So remember when you take the electron away, you have to examine what kind of atom do you have. Do you have the group of A atom? Do you have the other type of atom? So we usually think about either group of A, group 1A, group 2A, group 3A, or some of those so-called transition metals. Transition metal, even though you put the electron, the last electron you put in are those N minus 1D. But you take the electron away first from those S. So we'll see one example here from this on this slide. So now we have both the anion and the cation, so therefore we will see with a better summary. So Al3 plus, and by the way, once you have those electron configuration, and you can figure out whether all the electrons are paired up. So here means all paired up, and this means that some single electron that is not paired up. So if all the electrons are paired up, we said that is diamagnetic. If there are any like those single electron left over, you don't have to have too many. Even though you only have one electron that is single, and that will be paramagnetic. All right. So the first one is Al. So let's see, like Al is number 13. You first have to write the electron configuration for the Al. You're starting from like 1s and 2s. Right, so then let's see, do you need 2p? Yes, you need 2p, right? And then you also need 3s and 3p. Right, so you have 2 electrons in 1s, 2 electrons in 2s, and 6 electrons in 2p, and 2 electrons in 3s, and 1 electron in 3p. Alright. So then how you take the electron away? You take the electron away, first decide the group. If it's A group, you use A group pattern. And so this AL is group 3A. So therefore it's A group. For the A group, and you will take the NP first, then NS. What N? N, what do we mean by the N? N will be the highest N, the largest N in the configuration. Now, the highest N. For this example, the highest N is what? 3, right? See the highest N for the configuration of the AL atom, right? Is 3, right? Therefore, 3p1 first. If you take 3p1 away, so you will get 3p0. And that can only give you Al1 plus. So you need Al3 plus. That means you need to take 2 more electrons away. And so what you do then, it will be the 3s2. If you take a 3s2, and that becomes 3S0, and then altogether that will give you AL3 plus. Alright, so that is one example of the electron configuration for the cation, for the positive ion. So the next problem is solve for 2 negative. You already see the example before. Because it's 2 negative, so it have 2 extra electron than S. Right, so therefore to get the electron configuration for S2 negative, you just get the S first. S number 16, 1S again, and 2S again, 2P again, 3S again, 3P again. Right? Right, so 2, 6, 2, 12, and 4. So this will be the configuration for sulfur atom. Because it has like 2 extra electrons, so that becomes sulfur 2 negative. And so where you put these 2 extra electrons in, pretty much similar as what you do for the neutral atom. You put that into the lowest available orbital. And obviously the lowest orbital, that is 1s, but that is already taken. So right now the lowest available will be the 3p. Right? So you have 1s2 and 2s2, 2p6, 3s1, and 3s2, and 3p6. Right? You can write like this, but there are many different ways to write this, right? You can say because this is become same as what? So I said the same as, you can see that neon, then plus 3s2 and then 3p6. Or you can see because all together this become what element? All together. Yeah, they become argon. You can just simply write this is argon. Alright. Any questions? So this for the negative ion, we even did not tell the difference between the group, whether they are group A, group B. Obviously, group B is a matter of usual condition. You cannot produce a stable ions. Right. So the next one is about Fe3 plus. And to get Fe3 plus, we need to see this will lose 3 electrons from the Fe atom. Right? So when you take electron away, as we saw on one slide, just you have to identify what kind of atom you have, right? So let's first identify the group number for this Fe. Fe is group B. Is not group A. Group B tell you it is a transition. It is the transition metal. Now for all those transition metals, no matter they are regularly or some of those exceptions like the chromium and gold. So no matter what are the configuration, you just take the NS first. Sometimes that does not make really sense. Get that? So therefore, you first identify the configuration for the Fe. we start with 1s, 2s, 2p, 3s, 3p, 4s. This time we need this 3d. Okay? So let's add in the electron on. And we have 2, 2, 6, 2, 6, 2. And Fe not exception, so I will add in all the electrons just regular like that. Right? Now the problem is you want to get Fe like 3 plus. So we need to take 3 electron away. Right? If you pay attention to what I was doing, when I write the electron on, this 6 electron is the last 6 I write. That means it's kind of we adding this 6 electron the last step. So if you play some of those like the card game, you stack in the card like 1 by 1, and so you probably will take this electron first. Now I will tell you, you don't do something like that. Okay? If I use Euclid notation to write, so this part is argon. So I'm going to just write this is argon. And you will see if you write something like this, you need a 3 electron away, and you become like this, and this is totally wrong. It's totally wrong. But this is a very easy mistake. And that's a very easy mistake. Because you think it's a kind of usual sense, because you add in this 6 last few steps. Right? So now why don't you just take this, take 3 from this 6 away first? Right? And one kind of very naive, straightforward explanation for this is what we talked about last week, inside or outside. So even though the 3D orbital, the energy is a little like higher, but actually those 3D orbital, the physical location is a little bit inside the 4s. So 4s physically is more accessible. Right? And so therefore T electron away not only depend on the depend on that, depend on whether your energy is higher or lower, and you have to see it is valid or not. If you have an electron that has a very high energy but it's stuck in the middle, inside the other electrons, and you cannot take that out. So what you do, you will see this configuration. You still have the iron, and you are going to take 2 electrons away from the 4s, that becomes 0. If you only take 2 electrons away from the 4s, that only gives you, so then just right. So if I do this, if I keep all the 6 on the 3D. Now this configuration is for the Fe2 plus. Got that? Fe2 plus. Now the final result. So the final result, you want to get Fe3 plus, you will have 4s0, and then 3d5. And obviously, if you have a 0, you don't even have to write. So this will equal, or I just write arrow that you can write as same as argon and 3d5. Okay? So this will be our final result. Right? And you also want to know like how you produce Fe2 plus. So sometimes I might ask you to write the configuration for the Fe2 plus. Fe2 plus, that means you take 2 electrons away. Okay? And you only take these 2 away. You don't even have to bother with those electrons. But never take them away first. Okay? You only take 1 away from here because the problem tells you you want to produce 3 plus. Okay? You take these 2 away, and not enough, that only become 2 plus. You want to get a 3 plus, so therefore you take one more away from the 3D. Right? Question?
This one's a diamagnetic or paramagnetic?
Oh, good question. I totally forgot about that. Now let's see that AL. First thing is this one. Is this a pair of die? This is a pair. Okay? While this is a pair, you know this for the Fe3 plus. Okay? Fe3 plus. So this is Fe3 plus. Okay? Fe3 plus. So we have here argon noble gas. For the noble gas, for any of the noble gas, all the electrons are paired. Right? Now, so therefore, what you want to examine is to see what is the arrangement for the 3D phi. Right? So 3D phi, if you think about you have this, let's say you use the orbital diagram. Okay? 1, 2, 3, 4. So you have 5 squares. Okay? So what will be the arrangement for this 5 electron? Very good. So then according to the Hamilton's rule, so 1 electron in 1 orbital like that. Right? So if you know that the 5 electrons spread out, so that tells you have 5 single electrons. So we talked about before, if you only have 1 single electron, that will be enough. So any atom or ion or molecular, if there is 1 single electron, 1 or more single electron, and this kind of result is paramagnetic. And this material is attracted by the magnet. You can even like, you will see some of the picture. Okay? You can see that in between, hanging in between like 2 magnets. Right. So what about the first 2? What about sulfur? Do you remember what is the electron configuration for sulfur are 2 negative? Let me erase this here because that's irrelevant. As 2 negative, what is the electron configuration for that? That become simply become argon, right? Or it become neon with 3s2 and 3p6. Any noble gas configuration, we have like all the electrons are paired. So the result for sulfur 2 negative is diamagnetic. Like that. So this sulfur 2 negative, diamagnetic. What do you think about the Al3 plus? Do you still remember the electron configuration for Al3 plus? That becomes what? Become neon. Yeah, very good. Yeah. So for those group of A elements, after you take the electron away, put the electron on, and possibly they become the nearest noble gas. Well, obviously sulfur, for this example, sulfur 2 negative, that is very simple. But when you have some of those sulfur like sulfate or sulfide, and that becomes very tedious. So you use this simple approach, and you cannot decide. We have to see that in chapter 9, chapter 10, and when we have those Lewis data structures, maybe Lewis data structure not enough. We have to use some other theory like the molecular orbital theory, molecular orbital bonding theory. All right. So these 2 ions, both of the 2 is diamagnetic, because they end up with the electron configuration of a noble gas. All the noble gas is diamagnetic. All right, very good. So any other questions? All right, so you do a CRE, do a very quick practice. You want to write electron configuration for the cobalt 2 plus, and the cobalt is not accepting, so you can pretty much just pile the electron onto the cobalt first, and 1s, 2s, 2p, 3s, 3p, 4s, 3p. But the problem is the cobalt 2 plus, so be very careful how you take the electron away. What electron you take away first? The answer is A.
B.
I think Crystal is right. The answer should be A. Yeah. So I not emphasize enough. Okay? So Crystal, how you get A? You want to compare right up how you get A? What is the electron configuration for cobalt? Come here.
I just,
Right.
well, I didn't know how to do it. I just like thought from the last example that you took out from the 4s instead of the 3s.
Because this cobalt, if it's group A, you will take those NP first. Okay? Now cobalt is group B. That's how you get it. For group B, okay, they are not a group A. Okay? So for group B, you will take that NS, then N minus 1D. That's, as I said, that kind of very strange because if you pay attention to what I do for this cobalt atom, okay, for the neutral atom, and that's why you get like what fun and what you did is you observe like what I put those electrons on the P last few electrons. Very good. So you very alert. You pay attention to like what we did the example. Now again, let's see the electron configuration for the CO neutral atom. So we have 27, right? So let's start from the user ED notation. So use like the previous noble gas, and then plus what's beyond the noble gas. What is the previous noble gas? Previous noble gas for cobalt is what? Is argon. Okay? So we write argon first. Argon is in what period? What period is argon in? Number 3. Okay? So once you finish argon, that means you already finished your 3rd period. You're going to start on the 4th period. So you start on the period, you just use a new number. You have 4. Okay? Like for what? For S. Always start with a new period with S. Right? And you might use D, or you might just jump over to the B. But starting on the 4th period, you're going to use the D. Right? Now just be careful. The D, the number for D, right, is the same as the 4 or same as the period or less. One less. Right? So therefore we have the 3D. So you get those orbitals first. For most of the atoms, just pile them up. Just use lower one and then higher one. There are a few exceptions like chromium and molybdenum and so on, right? So cobalt is not exception. And you need how many electrons for cobalt? 27, right? This is 18. Now you get 20 now, right? So therefore you put 7 here. Now if you see what I did, that makes sense. You will see like you choose like this B. Right? Now even though B is not right, because when you see usually like what we did, we think about that we adding this 7 electron at the last step. So that means you will take that away, you take that away from the last step. That's even side again. For this kind of atom, or those kind of, we call them, those group D, or the transition metals. Very good. So you take this away first. Take them away first. Take what away first? Take those guys away first. Maybe 4s, maybe 5s, depending on the element, right?
So whichever is the highest?
Yeah, whatever the highest n. You take the highest ns first for the transition metal, right? For the transition metal. For the like the Al, right? Magnesium, they are group A. For the group A, you will take that, if they have the electron in the P, take the highest P first, then the highest S. And not that difficult, right? So let's see that. I think that's enough. So now you use this one, right? And you see here, for the Al, for the Al, even though that doesn't matter, you take this two away for Al. Where's Al? Yeah, Al is here. So for the Al, even though you take the S first, all the P first, for the 3 plus doesn't matter, because that's any of all become empty, become 0. But technically, which one you take away first? You take away from that 3P first. Right? I think let's see if you really get it or not. The result is A, right? Right, so the answer is A. And now what will be the configuration? Let's say if we have, if we want to produce CO3 plus, if I want to produce CO3 plus, what will be our result?
Wouldn't be AR, 4S, arrow, 3D, 6?
Very good. So you get a 3D7, so that means you take a 2 electron away already from the 4s, that becomes 0. Right? That gives you only like 2 plus, right? You want to get a 3 plus, you just take 1 more away from this. Now you're starting on the D. You're starting on the D. And this is optional. You don't have to write this because it is 0. So this is same as argon and 3D6. And same for this. Okay? And this you don't have to write this either. Okay? Now let's finish this why this is a paramagnetic. If you have this 3D7, why that is paramagnetic? 3D7 that means you have let's see how many orbitals in those D subshells? Yeah, 1, 2, 3, 4. So you have 5 squares, right? So you have a 3D7, and just put 1 electron in 1 first. That will give you 5 electrons. And obviously you have to put electron in to make a total 7. So what you can do, you can only pair them out, beginning to pair them out. So you pair one up, you get 6. And pair another up, you get 7. So after you pair 2 up, you still have this 3 single. So if you have 1 or more single electron, your atom or ion is called paramagnetic.
Wait, so if it's 1 or a single electron, it's paramagnetic?
1 or more.
Oh, 1 or more.
Yeah. not only one. If you have two, it's also okay. Yeah, one more. So if you have three, and in this case we have three. Sometimes the maximum you can might have like 7 or 5. If you have some orbital in F, you have 7 of those orbitals, and all the 7 electrons spread out. Very good. So I want you to keep concentrated and keep a very sharp mind. Now write the electron configuration for N3 negative. And by the way, this kind of review what you studied in chapter 2. This guy, if you have N3 negative, you call this is nitride, IDE. And if you have NO3 negative, what do you call that? Nitrate. What about if you have NO2 negative? Yeah, so those are very, very basic skills. Yeah? And you have to know the name for the ion, for the compound. And those obviously will be on the final exams. Right. So this is N3 negative. N3 negative. And so what will be our N3 negative?
Is it C?
C. Okay. Why? What is the difference between C and D and E? All looks very similar, right? I think C is the right answer. C is the right answer, right? Very good. And you get this starting from the configuration for N by itself. So C is the right answer. So why? So therefore, why not D? I think compare C and D, the configuration exactly are the same. The parallel or diamagnetic, right? So if you have this kind of configuration, like either C or D, and all the electron, that means all the electrons is paired up. All, right? So for this kind of configuration, either this one or this one, that tells us all the electrons are paired. If all the electrons are paired, that means your ion or atom is diamagnetic. Is that? Now why not E? Why not E? Anyone see why not E? This word is okay. Diamagnetic, why not E?
Because it's got helium or neon instead of helium.
Right. I think these two contradicting, right?
Yeah.
So there's not an or. So that's right then. So this should be like the helium. Like that? And compare this one with the cobalt 2 plus. Okay. Now this one is the Ca2 plus. Ca2 plus. That means you have to first figure out what is the group. Is this group A? If the group A, use group A's way, which means you take the NP and then NS. Is D? Yeah, I think that's. Everybody agrees D?
Yes.
Very good. So it's D, right? Alright, so we are going to study another pattern. Okay? So this chapter and next chapter is about patterns. Okay? Change in the ionic radius. Okay? So I'm going to talk about 5 things about ion's radius. So first of all, ion in the same group have the same charge. Right? You see like some of the examples. There's an example. Right? Ion same group have the same charge. Let's see the group 1A. Group 1A, not H. Okay? So emphasize, even though H is on the top of group 1A, but we don't call H is group 1A. Okay? The first one is the Li, and then you have sodium, then potassium, and then rubidium, and then cesium. Right? So what is the charge for this group 1A? That's what we studied like early chapters. And also in this chapter we have a little better understanding. What are the charge? All of them has 1 plus. Right? 1 plus, 1 plus, 1 plus, 1 plus, 1 plus. And that's one example. Okay? And the ion in same group have the same charge. Right. Alright. Let me use this. Ion size, so because they have the same charge, so therefore you can compare them relatively easy or make sense. The increases down the group, from top to bottom. This is kind of the same as for the atom, right? Remember for the atom, from top is smaller and bottom is bigger. On the left side is bigger, the right side smaller. So that's the same as that. The reason for the ion at the bottom is bigger because we have a higher valence shell. Alright, so another pattern is about compare the cation and also the anion with the neutral atom. Okay? You get this ion from neutral atom, and you saw like from when we run the electron configuration. So you want to get the configuration for Ce2 plus, you get the configuration for Ce first. Right? Then you take the electron away, you get 2 plus. Take 2 electron away, you get 2 plus. And you also see that the configuration for N is 3 negative for the nitride. You want to get 3 negative, you have to put a 3 extra electron on. So that tells us we can compare the ion with the neutral atom those ions come from. Okay? So that's what we try to compare. Do you think that makes sense? The cation is smaller than the neutral atom. For example, you just saw you have that Ce2 plus. Ce2 plus comes from Ca, that's the neutral atom. Right? Now which one is bigger? Which one is larger in terms of the radii or radius? Ca, so you just see that. So that Ce2 plus is smaller than. Right? Ce2 plus is smaller than, so this sign. Right? Smaller than. Right. Now the other type is the anion. Right. You just saw in the last example. Okay? So you have N, okay? And N 3 negative. Right. So you get N 3 negative from N. Now which one is bigger? So again, this one like this. The N is smaller than the N3 negative. Right. So let me just read this. So then all the pretty much most of, you can see all of them, you can see the except, but the better way to say most of those cations, okay, is smaller than the anion. That is a very, very like larger statement, which means no matter what kind of cation, for most of the cation, they are smaller than the anion. There are some of those anions are very, very small. Right? What kind of anion is small, it just depends on the atom. Right? There are two very smaller anions. One is F1 negative, right? And the other one is O2 negative. So this is the fluoride, and this is the oxide. Right? Because the atom in the upper right corner, fluorine is the smallest one, so if any one electron on, the fluoride is still small. Got that? And on the other side, on the left lower corner, so those atoms, so on that side, so those are the larger atoms, right? So those atoms here, so this is the largest one, or francium, the largest one, right? So you take the electron away, they are still like kind of big. But you can set these few concentrations, like this rubidium and the cesium, okay? These are the cations. Take electron away, make them smaller than, so this Rb plus is smaller than the Rb atom. But because Rb is starting from something that's so big, right? So therefore you still like bigger than those. You're starting from something small, even though that make them still bigger than the neutral atom. So get that? Right. Now you can see the other pattern, the last pattern are emphasized in red, because that is a little difficult to identify. And then this last pattern, you can even like compare in between two different periods. So most of the pattern is compared in the same period, going from left to right in the same period. Now this last one are emphasized in red. You can even compare those in two periods, as long as they have the same electron configuration. And obviously, in order to have the same electron configuration, the minimum requirement to have the same electron configuration is to have same number of electrons, right? To have same number of electrons. If you identify, if you have some question, ask you which one is bigger, which one is smaller, you see they are not in the same group. So therefore, you cannot say if the one on the top is smaller, the one on the bottom is bigger. You are not compared like Na with Na plus with Na. So those previous pattern cannot have a solved problem. Try to like think about this last pattern. So if I give you 3 something, okay? See that 3 something, not in the same group. Not like the calcium and calcium 2 plus and calcium, like just you can't, calcium 2 plus come from calcium. So those previous patterns you cannot decide. So what you do, you just try to check how many electrons do they have. If they have the same number of electrons, then you can use this last pattern. So there are two patterns you can use. And that means the larger the positive charge, and then the smaller the ion, or the larger the negative charge, the bigger the ion. You can also summarize these 2 statements into one statement. That means the larger the atomic number, the smaller. So depending on what you like, you can just obviously you can compare the larger positive charge and larger negative charge. Okay? But you can just identify few those ions, maybe positive ion, maybe negative ion, or maybe even neutral atom. So you have a few of those guys together. You want to compare who is bigger, who is smaller. Okay? If you identify they have the same number of electrons, and obviously all those still have the atomic numbers, right? And then just identify who has the largest atomic number. The one has the largest atomic number, it will be the smallest radius. Right? So this is about the ion patterns, ion radius. Right? It kind of becomes tedious, not so simple as those atoms. Right? And I think this table has a lot of those. We can see the review what we did in on the last slide. Last slide we talked about the first pattern is the ion in the same group has the same charge. You see that? Right? Ion in the same group has the same charge. In general, that is true. You can see here, group 5A, 3 negative, 3 negative, 3 negative. Group 6A, 2 negative, 2 negative, 2 negative. Group 7A, 1 negative. And group 2A, 2 plus. And group 3A, 3 plus. And even though there are also some other charge, but as I said, most of the time they are good patterns. Group 1A, 1 plus. Okay. The second pattern on the last slide, we talk about the ion in the same group from top to bottom, the radius getting bigger. And you can see from the data. Okay? So we already see the examples for this. We don't have to worry about that because that's not group 1A. From top, lithium 1 plus, to the bottom, cesium 1 plus. You can see those numbers is the radius in angstrom. Angstrom is 1 unit, which means 10 to the negative 10 meter. Right? Top is smaller and bottom is bigger, so this is one pattern. Okay? Then we talk about the pattern, compare the ion with the parent, with the neutral atom. Okay? That pattern is the positive ion is smaller than the parent. The negative ion is bigger than the parent. You can also see those pictures. That we don't have those data here, but on the next slide you'll see that. Right? Another pattern is for most of the cation, for most of the positive ion is smaller than most of the negative ion, except that these two, compare with these two, and let's see that's true or not. That's true. Right? See, oxide, O2 negative, 1.40, F1 negative, 1.33. So for all the other negative ion, they will be bigger than all the other positive ion, except these 4 guys. Right? Now the last pattern we talk about is the sort of iso electronic series. You can just examine what we said the minimum requirement. What is the minimum requirement for this iso electronic series? A series, which means you might have 2, 3, or 4 those different ion or atom. What is the minimum requirement for the iso electronic series? They have to have the same one.
Electron configuration.
Yeah. Or have the same electron configuration, that means they have the same number of what? Same number of what? Same number of electrons. You can skip one step. You don't have to check in what other configuration. If you want to see the configuration, you have to say 1s2, 2s2, and so on. Obviously, usually that will be true. Right? You just examine how many electrons do they have. Right? If you find out like a few, those ion, positive ion, negative ion, they have the same number of electrons, and then you just use what I told you on the last slide, okay, and find out the increasing order of atomic number. The larger the atomic number, the smaller the ion. Right, now, try to find out, see if you can find out from this table, let's say find out 6 ion that is isoelectronic. Find 6 ions that is isoelectronic. What do you say? Which 6 is isoelectronic? But many, a few like a group of 6. Okay? So if you can find about one group of 6, and that is isoelectronic. Find that means you will find out how many electrons you have. Anyone find a 6 ion that has the same number of electrons? You can start with someone that has some number of electrons, and you go like either to the left or to the right. You can even jump in the row. You can even jump in from the first row to the second row. Let's see how many electrons they have.
Is it gallium and +1?
Okay, you start with the gallium, Ga. Okay, let's start from this. So G is, let's say 3 plus. Okay, forget about this. Okay. So G 3 plus has how many electrons? Twenty-eight. So those, I probably did not tell you, those same number of electrons, which means same number of same number of electrons, same number of valence, and you don't have to worry about those inner electrons. Right? Yeah, if you see that kind of look like confusing because G has 31, 28, so that's right? And then kerosene, obviously, that is 2 plus and become 18. So that's obviously, they don't have the same number of electrons. But they have the same number of valence. And they don't have the same, they don't have the same configuration either. But you will see this G3 plus will have that 3D10 in it.
More about lithium and radium?
Yeah. So forget about this little tedious. I think that we did not see that very clearly, and just see because that become very tedious if you have to examine the valence electron. Okay, Just use the first few and examine those neighborhood electrons. Those are very, very easy. That means you including those total electrons are the same. Right?
So it's the total electrons or the valence electrons? Now I'm confused.
Right, that's, yeah. For all those atoms, for all, any of those atoms, and we very use the valence. It's valence electron. Same number of valence electrons. All right. So let's say find out one and lithium, you don't have here. For lithium, there's only a few. You probably will not have that. What I said, 6.
So lithium and helium is correct, they are
Lithium and what?
helium?
Yeah, lithium and helium is that correct? Lithium and helium is correct. All of them will have 2 electrons. I mean lithium 1 plus, right? Lithium 1 plus. So here we have helium, and then we have even have here beryllium 2 plus, and then boron 3 plus. Yes, that's good. Then you have 4 of them. Right? So you don't have. Then let's see compare these 4. Right? Use what we said. We don't have the number for helium, but let's say we just have these 3. These 3 we already talked about the pattern. So these 3, what is the one line I tell you is you don't have to worry about the positive, a lot of positive, a lot of negative. Just find out the atomic number, right? What I said, the larger the atomic number, the smaller the radius. Is that right? What is the largest atomic number? Let's compare. Forget about the helium because we don't have the data, right? Compare these 3. Which one, lithium, beryllium, and boron, which has the largest atomic number? Boron is number 5, right? Yeah. So that we agree this all these have the same number of valence electrons. And that is true because you take those away, and lithium you have 1s2, and then you have 2s1. So if you take this away, what left over is 1s2, and that will become the highest shell. The highest shell that means you only have 2 valence. That's my overview. Right. So let's see this. So that's right. So there's 3. The largest one is the largest atomic number is the boron, right? Right. Find out another. Let's find another one. If you want to do, we probably don't have time to like really analyze gallium and lead. Let's find out. So let's see from the other 2 rows. Which one is isoelectronic? The same number of valence electrons. We can start with, for example, here, carbon. And carbon 4 negative tell you how many electrons in carbon 4 negative. Total, now this is total. But those, they don't have, if you don't go through the middle of the transition metals, you don't have to worry about that, just see the total. Right? How many electrons in for the carbon 4 negative? 10. And how many electrons for this N3 negative? Right? All 10 here. Right? And how many electrons for the sodium 1 plus? 10. And how many for magnesium 2 plus? 10. And how many for aluminum 3 plus? They're all 10, right? Right. So that is pretty good. So these 10 electrons, and you can even either them, they also have the same number of valence. Right? So therefore, let's see. So I will circle this field, so that's this field here, right? And we are even in different periods. So this field in the second period, this is what? Third period. Right? But the important here, we talk about they will have the so-called the same electron configuration, not exactly the same, or the same number of electrons. Right? Alright, so what I'll tell you, once you identify that, you find out the what? The largest atomic number. Right? So which, compare these 6 I circled, which one has the largest atomic number? Which one has the largest atomic number? Compare nitrogen with oxygen, with fluorine, and then sodium, magnesium, and aluminum. Which one? Aluminum. So then what we said on the last slide, the one that has the largest atomic number will be the smallest ion, no matter they are positive or negative. See that? Right, I think that's enough of that. The other pattern I said compare the ion with the parent. What we said is the positive ion is smaller than the parent. You can see here. These three columns. The positive ion, lithium 1 plus. So this one in the middle. And then this is the parent atom. Right? Now the other ion, these 2 arrows you already saw before. Okay? These 2 arrows, one arrow going from up and down. So that means it's the same group of ions, and they either like 1 plus or 2 plus or 3 plus. Okay? If you compare those, obviously from top to bottom getting bigger. Okay? Now this arrow that means you draw from right to the left. Okay? And you compare those the so-called isoelectronic series. Okay? So even though they have a different charge, okay, but they have the same number, so-called same electron configuration, or same number of electrons. Okay? Right? And you can see the pattern going from this side to the other side is getting, those ions getting bigger. That same as what we said for the atomic number. You compare, for example, you already see that lithium, beryllium, and boron. Boron has the largest atomic number, number 5, so therefore it's the smallest one. So the negative ion, and negative ion can also compare with the parent, negative ion and the parent, and you can also compare top to bottom if they have the same charge. You can also compare from left to right or right to left. Right? So what do you think that you compare like the negative ion with the parents? Who is bigger? The negative ion is bigger or the neutral atom is bigger? Negative ion is bigger. Right? Now if you have the same charge from top to bottom, all 2 negative or 1 negative, from the top to bottom is getting bigger. Okay? Or you see like they don't have the same charge number, but in the same period, they have the same number of electron, same number of valence electron going from right to the left. Okay? And then the one on the right is smaller because the one on the right in the same period has a larger atomic number. Right? You see the numbers. See here, fluorine 136, and the F1 negative is 136, and O2 negative, so they're getting a little bigger, 140, right? So now you have this. So ion pattern is little difficult to compare. So choose larger atom or ion from each pair. So the first pair you compare sulfur with sulfur 2 negative, right? So you compare sulfur with sulfur 2 negative. What you use a pattern of the ion with the parent, right? Ion with the parent, where the ion come from, right? So we know the anion is bigger than the parent because that's you adding some electron on, right? That? So therefore, you want to circle which one is bigger, you will circle the S2 negative. Right? So then the positive ion is smaller than the parent. Right? So therefore, we will say this calcium atom is bigger. Right? Now these two, they are not parents, not a parent, not like in the same group. What do you think? What should you use to compare these two?
Atomic number.
The atomic number, okay? Or the iso electronic series. Right? These two are the iso electronic series. What do you think? These two are the iso electronic series. And right, so they are iso electronic series. Valence electrons. So that's valence electron is very important. Right? So how many valence electrons in like the for these two this is the same. The valence electron number is the same. But I can show you this, you compare the valence electron, they will be the same. So therefore, which one is bigger? The Br1 negative is bigger. Right? So once you identify they have the same number of valence electrons, and you see the atomic number is, if the atomic number is larger, then they are getting smaller. Ooh. Right, so choose larger atom or ion from each pair. Let's see, let's do one by one first, okay? So what do you think? Between K and K plus, which one is bigger? That's easy, to compare with the parent, right? So K is bigger, K plus is small. Because not plus electron, plus that means you take electron away. You see plus, no plus what? Plus that means you take electron away, okay? So then compare F with F1 negative. So F1 negative is bigger, okay? I see, so that's a little easy confused. So you see, probably you get opposite, F1 negative means you subtracting means not but the opposite, okay? But, so plus is bigger, F1 negative is bigger. Then the last two, how you compare the last two, Ce2 plus and Cl1 negative. They are not the parent, they are not in the same group. How you compare this last two? Yeah, so you have to use the iso electronic series. Right. So these two is no problem. So they were adding up with the same number of electrons anyhow. So you don't have to worry about the valence or not. Otherwise, you have to check the valence. So how many total electrons for both of them? How many electrons we have for Ce2 plus? So even though this one, the total electron is also okay. Right? Total electron has become what? Become 18, right? So this one saw that 22. So then how many electrons this one will have? Let's see. Right. So therefore they have the same number of electron. Right. So then the larger atomic number, who has a larger atomic number? Cl is 17, right? And then Ca is what? 20. So the one that has a larger atomic number is smaller. So therefore this Cl negative is bigger. I think this makes sense, right? Okay, so that's what we, alright, so what do you do about this? Think about this three. C2 plus an iron and a Cl1 negative. Put them in the order of decreasing. You want to find out one that is the bigger one.
Is it big?
See?
Right, so I hear B or C. And other choice. A.
E.
Well, we think about what is. I think why is E?
Because the negative would be bigger than the positive, and then you have the regular one. Or no, it'd be B.
You change your mind, B?
Yeah, it's B.
So you not only compare like the positive with negative, because you compare positive with the parent, you have to see the parent. Right? So one of them is like you have the C2 plus is not a parent of or like the or something from anything else, right?
What do you see from C, is it increasing?
Yeah, you want to. This one is a decreasing order. You want to find the big one first. Find the big one first, right? I think B is right. B makes sense, right? I think that is the common mistake in this chapter. So you have to see like whether you want to find the decreasing or the increasing order. So decreasing order, that means you want to find the bigger one first. So the answer is D. Right, so now let's go on to the next section about ionization energy. So we already talked about how to take the electron away and how to add the electron on. And then for both processes, we are going to talk about the energy that's associated with it. Okay? So when we take the electron away, do we need the energy to put it in? And when we put the electron on, do we need to put the energy on and so on? And so then we also compare those. We'll find out also a pattern for that. Get that? Now this ionization energy, so the first letter is I, and then this is E. So therefore we simply call that IE. So you, in this chapter you will hear me a lot about IE. IE, that means ionization energy. And then you also will hear me a lot about IE1 or IE2. What that means is IE1 is remove the first electron. And IE2 is remove the second electron. Get that? And then what is IE3? Remove the third electron. Now you have to see like a little more precise. Okay, remove electron from what? From those gas atoms. And remove electron is always an endothermic process. So then we also know the valence electron is the easiest one to remove because they are in a higher energy orbital, and physically they are easy access. So the general chemical reaction equation is given by this. And this M is not a really element, it's a hypothetical, is a generic name. So this M, right? So let's say Mg, which means atom in gas state, plus I1. And I1 is the so-called first ionization energy. So our image side here, I1 equals our first ionization energy. Got that? So I1 representing the first ionization energy. It is representing one part of energy you put into this kind of equation and produce +1 ion in gas state and +1 free electron. You have to know what is the equation, because in chemistry, the equation is very important. So what process has what equation? IE2, what is IE2? IE2 equals second ionization energy. You will see the consecutive step. So you will take the product from the IE1 as the reactant for the IE2. Right? So you will take that Mg1 plus, which is the product of the first process, and adding more energy, you will take another electron away from that 1 plus. If you take 1 electron away from the 1 plus, you get 2 plus. And in the same time, you produce another electron. Alright, so we do a practice right here. So what will be the equation for the IE3, or the third ionization energy? And we will still use the hypothetical element N. And it shall be in the gas state. So this gas, this G is gas. Alright, so what shall we start from if you want to see the equation for the IE3? Start from the M1 plus, start from the M neutral, or start from the M2 plus. You want to remove the third electron. You will start with what? The 2 plus. Right? And then plus something, and what you will produce. So this M is symbol here, M. If you remove 3 electrons, and this M become M what? 2 plus, 3 plus. So therefore this will be 1 extra electron here. Now what energy are you going to put here? This will be IE what? IE3. Alright, so this is the general pattern for those equations for the ionization process. Okay? You have 2 here, IE1, IE2. They can continue with IE3, IE4. If you have those much electrons, obviously for some element you probably don't have that 3 electrons. And so then what is the pattern is for the, you can think about for the IE. Obviously you can compare the IE1 with IE2 with IE3 for the same atom. And you can also compare the IE1 for the element in the same period. You can also compare I1 for those elements in the same group. Right, now let's first compare the pattern for the first ionization energy called I1. So in this comparison, and you will see very few, or you will see like three periods. There will be 6 pair of atoms that is not in the usual patterns. But let's talk about the usual pattern first, then we'll talk about some of those exceptions. Right, so the one pattern is you're going from left to the right, and the IE1. So the IE1 is getting bigger and bigger. So going from here to here, and this one will be the increased IE1. So I have to emphasize this is in general. That is very important for this pattern because it's not for everyone. And increases and in the same group. Increases. Right. Now I want to remind us. Let me write a different pattern here. Okay. So this is for the IE. For the atomic radii, okay, for the atomic radii going from here to here, what should be the direction for these two arrows? Decreases and decreases. Okay. So don't be confused. So these two patterns kind of opposite. Okay. So you have to see what you want to compare. Are you compare the radii, or you want to compare the IE1? So why those that happens going from left to right, the IE in general increases? That is because what we said before is a sort of the effective nuclear charge. So you gradually increases from left to right the atomic number. Then the sharing electron, pretty much those core electrons, and they are the same. So therefore, when you increase the atomic number, and you have more and more attractions. More and more attraction in general make them a little harder to remove the electron. But we will see there are 3 periods. There are altogether 6 pair of atoms that have some of those exceptions. Right. So you compare. This second paragraph is compare like the IE1 for those elements in the same column. In the same column, so you compare the electron, are they far away or are they closer to the nucleus? And then when you go from top to bottom, so the electron getting far and far away from the nucleus. So therefore, it's getting a little easier and easier to remove the electron. And for the IE1 or decreases. Right. So these two patterns, again, that is our usual pattern. Compare left to the right, top to bottom, or vice versa. Right. But this left to right, right to left pattern is not absolutely true for every pair of atoms. And you can see this picture tells you those patterns. And for the same group, as is those noble gas, and this helium is on top, and this is at the bottom. So bottom, again, the atom getting bigger, so therefore a little easier to remove the electron. The other pattern is going in the same period. So those are the same period. And it's not good. So in the same period, in general, in going from left, so this is our left side, and that is our right side. Right, left side and right side, so that's left side, the atom is bigger in general, that's a little like easier to remove the electrons, so therefore the IE number is little lower. And in general, the atom on the right side, the radius is smaller, so it's never difficult to remove the electrons, and so that is the pattern. But you see this two pair of atoms circled here. So this and four pairs, and you can see these two guys. If you see them carefully, they also the opposite. So these are the sixth pair of atoms that is not in our usual patterns. And the number probably even easier to see. Okay? So in general, again, we'll see this is increasing. This arrow is not good because it's 12 opposite. So this is the increase, and this is the decrease. You can draw either one, or just make them both are the same. And the exception are those. So here is group 2A, group 3A, group 5A, group 6A. Okay? And that one pair like this. Obviously, the number tell you very precisely. 899 is bigger than 801. Okay? But in general, that's our general pattern is going from that to this. Okay? So increases. So that's obviously is not the usual patterns. All right. So forget about those exceptions first. So the exception, I tell you that there are a few pairs. Okay? So let me finish this 6 pairs. So here is not exception, and here is not exception, and here is not exception, exception, exception. That's 6 pairs. Okay, so now we will see those exceptions. I will not examine you on those exceptions. I will just tell you the reason later on. So what I will give you the problem is without those exceptions, not those exceptions. Right? So this example is you want to compare AL with sulfur. Let's see, where are the AL and sulfur? So these two are on the same what? Same period. And the same period on the left side, okay, the IE1 will be smaller. You want to get a higher IE, so this sulfur will be the one on the right. But I said you don't have to worry about those exceptions, right? All right. So the next one is AS or SB. AS and SB. Probably easy to write that. AS on the top and SB at the bottom. So they are in the same what? Same group or the same column. All right, same column, the one on the top, there are not too many exceptions. The one on the top will have a larger IE. Right? So therefore this one is on the top, that has a larger IE. Right? Now the C is compare between N is here, okay? And then carbon is here, and then silicon is here, and then what? Silicon is here, then you have a phosphorus here. Right, so for those kind of problem, they are not same period, not same group. So you need 2 arrows. So I will draw 2 arrows. You can start from either one. You want to compare N with SI. Which one you want to start? You can tell me which one you want to start. You can start with anyone and just use those horizontal and vertical. Don't use diagonal. And you need 2 steps. Which one you want to start? You want to start with from SI, or you want to start from N? You say you want to start from N. Okay. Let's see which one you want to do. You want to do left and right, or you want up and down from N? Left and right first. Either way, let's do it left and right this way, right? So there's one arrow. And those kind of arrow is horizontal. That means compare in the same group. Then you know which one is bigger, right? So you go from N to C. Is it increase or decreases? Those are not. We don't talk about the exceptions. There's no problem with exceptions. In terms of IE1, so IE1, and this is a decreasing arrow. And obviously, you cannot sound that. And you have to see the other arrow will take you from C to SI, and this arrow is also what? So this first arrow is our decreases arrow. The second arrow is also what? Yeah, so that's also decreases order. Right? Well, so therefore, as what we did before for the atomic radii, and you have a conclusion, right? So that has a larger IE1, and silicon has a small one, because those arrows tell you decreases. You can start with any atom. You can start from, for example, like if I start with silicon, and let's say I want to do like to the right. You compare silicon with phosphorus. This arrow tell you what? Increase or decreases? Increases. If you draw from phosphorus to N, this arrow is also what? So if 2 arrow increases, therefore tell you N has a larger IE1. Now oxygen and chlorine. So we will see the oxygen is here, fluorine is here, and sulfur is here, and chlorine here. And now you want to compare this oxygen with chlorine. Now tell me which one you want to start from. You want to start from oxygen or chlorine? See, from oxygen? Okay, oxygen you want to go left or right or up and down? Either way, right? Go to the right. Okay, so go to the right. Now this is what kind of arrow? Increase. Very good. So that's increase. And obviously that was what we saw before. We cannot stop on that. And we have to draw another arrow to get a CL. And this arrow is what? Decrease. Yeah. So my arrow is increase, the other arrow is decrease, so therefore you cannot decide. Alright, so it's very, each problem is very simple. You just have to study a little bit to put everything together. Right? So arrange the following elements in order of increasing ionization energy. Increasing that means you want to find the one you want to get first is smaller or bigger. Smaller. You get a smaller one, then you can like to the more and more big one. What do you think? Any answer? Looks like there's no answer. We don't think about those exceptions, right? So what kind of atom will have the lower or smaller IE1? The one on the final answer is D? So why is D? And D is, I think D is right. So you want to find one that has a smaller, so increasing order. Increasing order, that means you want to find what? Start with a smaller IE. So why D is right? So D is starting from potassium K. Potassium K, the potassium K, those kind of atoms, do they have a larger radius or have a small radius on that part in general? They have a lot of radius. They have a lot of radius. They have a lot of radius. Because they have a lot of radius, the electron is never far away. Okay? So easier to remove. Alright. So that's about this problem. What do you like? Do you like chemistry because there's a lot of conservative or because there's a lot of numbers? Chemistry is never like everything, right? Never conservative, never numbers. So what is this? So I give you like 4 pairs, right? And you want to choose, if you can, the one that has a higher IE from each pair. Is D. Okay. Who said it? A.
I said yeah.
Is this a year D?
I said yeah, in agreement to do.
Okay, yeah, D, let's see the D right. I think the first one, compare Sn with I. Sn is here, I is here. So as I said before, you don't have to worry about that exception. There are 6 pair that's not in usual pattern. That means you're going from left to right, not the increases, there's a little drop. Yeah,
Why is for C and P, it says that you decide?
okay, why between C and P cannot decide? Just draw 2 arrows, okay? Just draw this way and this way. Okay? If you do 2 arrows, you just go like all the way. Let's see what we have. So that's a good pattern. And let's circle this C here, and circle this P here. Now let's take 2 arrows. Okay? And you don't use diagonal. Okay? So let me read this. So I will first go from carbon, okay, and to nitrogen. What kind of arrow is this? Is this arrow increase the IE1 or decrease the IE1, going from left to right? Yeah, for the IE is increase, for the radius is decreasing. Okay? So this is the increase. And you cannot say, you have to go all the way to the atom you want to compare. If you want to compare C with P, therefore you have to like go all the way from C to P. So you just go from N to P, right? Then N and P in the same column. In the same column from top to bottom, and this arrow is increase or decreases. So it is like a decreases. Right? Decreases the IE. You have the atom getting bigger, but because the atom getting bigger, so it's easier to remove the electron. And once you have these 2 arrows, if the 2 arrows tell you something different, you cannot decide. And you get that? Yeah. You will see that on the opposite. Let's see the other one, the other 2. Fluorine and sulfur is also not in the same group or the same period, right? So you want to compare these 2. So now this time let's starting from sulfur, right? And starting from sulfur, let's say we can either go up and down or left to the right. So let's say starting from sulfur, where you want to go? You want to go left? You want to go up, or you want to go to the right? Go to the right. Go to the right. this arrow. Okay? So going from left to right, forget all those exceptions, the IE increases. Right? So this is increases. Right? You have to go all the way to the arrow you want to compare. And then you go from CL to fluorine. This arrow is also what? Going from bottom to the top in the same group for the IE. The radius is getting smaller, but the IE is getting what? So you compare chlorine and fluorine, which one is easier to remove the electron? Chlorine is easier, fluorine is difficult, right? Okay, so that's okay, so this is the first time. So both arrows tell us the IE is increasing. So therefore we know this fluorine has a larger IE. Right? Any questions? Alright, so I give you like a few different ways to ask you the question. This problem, you have to read the question carefully, so you want to get the decreasing IE. If you want to get the decreasing IE order, that means you want to starting with one that has what? Has the highest, has the largest. That's why I think that's, you can those, that's good, that's E, right? And E, fluorine has the, you still can check all the others is right. Fluorine is larger, is on that right corner than sulfur, and sulfur is to the right to silicon, and silicon is to the right to calcium, and the calcium is on top of top and right of the radium, therefore that's. Right, now we are going back to examine those irregularities. So there are like 6 pair of irregularities, and all the 6 pairs that happen between group 2A and group 3A, group 5A, group 6A. Got that? And this is 3 pair here, so 3 pair here, right? And one more pair, one more pair, one more pair, and 3 pairs here, right? So I have 6 pair of exceptions, right? And it's very interesting to be able to understand those irregularities from that new model. Wow, what is our model? Is the quantum mechanics model. And the quantum mechanics model, what we learn in this class is to see the electron configurations. Right? Where are the electrons? In what orbital? Right? So therefore this is we are going to use the electron configuration to try to understand that 6 pair of exceptions. Right? And to see that exceptions in word, you will see the ionization energy in general increases from left to right across the period. You see that exception that this last slide? It's suppose this boron to the right, and sure increases IE, but it's getting smaller. And similar for oxygen on the right side. Suppose to get a higher number for IE, then you can see that the IE is getting smaller. You have 1400 compared with 1300. So those are sort of the exception to our pattern, or the irregularity. Okay, so we said that is because of the electron configuration. Okay, let's compare the electron configuration. For example, between one pair of atoms, that is between beryllium and boron. Beryllium is in group 2A, and boron is in group 3A. The electron configuration for beryllium tells you you don't have any single pair. It doesn't matter here, but just because this beryllium has sort of completely filled, and this one have one single electron here. By itself. So we noticed this pattern first, and then we were thinking about how can we use this pattern to explain. So we notice the electron configuration for BE, that's you pretty much has not really a noble gas configuration. Noble gas configuration, that means the 2s is completely filled. The 2p is also completely filled. So that's the one shell is completely filled. That's noble gas. Now this BE not really noble gas yet, because you only have this sour shell that is filled. The 2p sour shell is kind of empty. But according to the quantum mechanics, so if you have like a sour shell that is completely filled up, like in this example, 2s, and this is totally empty, that is a good configuration. That means your energy is relatively low. And the other one is opposite. You have that 2s is filled for the boron, but there is one active electron in the 2p. Okay? So those not ever really true for everyone, because you not only compare like those one active electron, you also adding one proton in it. So their energy, their orbital is not really exactly the same, but you can get some of those ideas. So then similarly, you can see compare the nitrogen with oxygen. Nitrogen has this kind of configuration, and oxygen has this configuration. Now let's see what is the difference between this and this. This one, so the 2s is filled up. 2s is 2s2, that means the maximum. Okay? And that's the same as this 2s for oxygen. What is the difference between the 2p for N and 2p for O? So for the 2p for the N is half filled, and you don't have any electron pair. Now for the O, you have one electron pair. The electron don't like to be paired either, because when you pair the electron, they will repair. Electron has a negative. So you just compare this, all the three single with like one pair, and this configuration is a little bit higher. Now compared to the higher and lower, for those process, it's better use what we learned in Chapter 6, those energy diagram. Right? So the IE pretty much is the difference. Is the difference energy between the beginning and the final, and what we study in Chapter 6. Right? What is delta? Delta means change. Change always the final minus the initial. Okay? Yeah, I added this like since like the spring, but I did not put it on the canvas. And so you remember in Chapter 6 you studied the so-called delta. So delta E, which means it will equals the E final minus E initial. Now for this beryllium process, so for beryllium, starting from beryllium atom, become beryllium 1 plus ion, and this is our final, this is our initial. Right? Now for boron, so this is similar. This is our initial, and this is our final. So this will be the delta E, and that will be the delta E. Okay? So then you compare the beginning and the beginning, compare the ending and the ending. So as I said, you cannot use this, every solution for all the atoms. Well, all the atoms not only compare those orbitals, you have to think about also their protons. Okay? Right? Do you agree like this kind of configuration has lower energy compared with this? I think that is trivial, right? This one is lower because you have this one is higher because this one you have one every electron that is in a higher energy orbital. We know the 2p orbital has high energy. So you put one electron in, and you put an electron in, put one electron in, compare there, there's empty here. So obviously your energy will be higher. So therefore, this line here is higher than that line there. That line is the energy for that. That's, you don't have electron here. Right? And now compare the finish. If you take this electron away, you have only these two pairs. Therefore, these two pairs. This is empty. If you take this electron away, you get this become like a half. Now this is difficult to understand because this is not your trivial experience. This tells you from the calculation that tells you for those kind of configuration, even though you have less electron, right? You have less electron here, there's only one electron here. Right? You're supposed to have less energy because you think about it, okay, I have more electron in there, and each electron have energy, that will make my electron has more energies. If I have less, it will have less. But according to our model, if for those kind of orbiter, if you pair them out like this, make them like half filled, or the normal gas become totally filled, the valence cells. So some model is very easy if you study liver like those models for some of those like the benzene molecular, those sort of Huckel's very simple quantum mechanical calculation. You take some of those atomic orbitals and do a little algebra. If all the electrons are filled up, and then some of those atoms some of those terms can come out. So even though you add electron on, not really make your total energy become higher, depending on where you add the electron. Right. So even though there's less electron, but because that electron is single, and make that become higher. Now that become higher, that become lower, that become lower, that become higher. So the gap between this for the boron getting smaller compared to the gap for that. Right? So as I said, I just found out from one faculty website why we study chemistry. Well, we study chemistry, even though you might study for like nursing, or pharmacy, or dental, or medical schools, you want to get the sort of the cognitive ability. What is the cognitive ability? Cognitive ability is use what you learn and be able to solve some problem. And that is related to the sort of the people sometimes call the IQ. So usual person has IQ about I think 100 something. If you have IQ like more than 120, and that means you are in a population of the people 90% higher. So there are some of those online exams. You can see what is your IQ. If your IQ is 120 or higher, that means you are on a percentile of 90. You are smarter than 90% of other people. So actually, what we find out is you can increase your IQ by studying some of those basic like those cognitive skills. So where you get those cognitive skills is from some of those science class. Because science class is you learn those fundamentals and use fundamentals to solve the problem. Right. So this is the general chemistry class. So you will see those kind of orbital diagram like in the organic chemistry, in some other chemistry class. And so similar idea compare between the group 5A and group 6A, right? Let's say group 5A element is starting from this nitrogen, and compare with starting and finish, starting with half figure, so that's a stable, so therefore this line lower. And you finish up with that and become higher, and then compare this opposite, so that become a half field, and if half field, that means it's stable, so therefore the line is lower. And this is not half field, you have one actually electron pair also getting higher. So I mean that is the reason. So you're starting from something higher, and you end up with something lower, so therefore you have a small gap for oxygen. Right, so that is about the pattern for some of those ionization entries and also those exceptions. Right, now we are going to see the other pattern for the IE1, IE2, or the IE. IE has a lot of you can compare. Right? So we are going to see the so-called successive trend. So that means we are going to compare for the same atom. And this kind of makes sense, and also kind of even use what we study in Chapter 7, those electron configurations. So remove of each electron become harder and harder, become difficult and difficult. That is because the shrink in the size, because you have more protons than electrons, and more attractions. And that's also because all the electrons getting closer to the nucleus, so therefore it's harder to remove. Right? Now, as you expected, okay? So you remove the first electron is easier than to remove the second electron. To remove the second one is easier than remove the third one. To remove the 3 electron number 3 is easier than to remove the number 4 if you have that much electron. Right? So you're getting more and more difficult. But you have to examine that carefully, and those increases, we call them regular increases. Regular increases to the most, you can increase like twice. Okay? Now those not regular increases or the larger increases. Those larger increases to the least, it will be 3 times more. Right? Now that is very important. So when you have the regular increases, that means you are removing those valence electrons. Regular increases, so you can write it here, is remove valence electrons. Right? So that's larger increases. It will be your first core electron. When you see that one large increases, that means why you have that large increases? Because you already removed the core electron. Alright, you can see it here. 2 elements here. One is the sodium, the other one is magnesium. You can see sodium, the first IE1 has about 500. And then the second IE, that means remove the second electron from Na, that should become like almost 10 times, 9 times higher, 9 times difficult. And then we don't call this a regular increase. Regular increase is, I said, to the most twice more, 2 times more. And you can see here this magnesium. Magnesium, the first one, the number is 738, about 740. The second one is about 1450. So again, compare the second one with the first one. That's regularly increases because that's about twice that much. But you compare this second one with this number 3. It's almost like 6 times higher. And that is not a regular increase. Then you understand why you have this 2 larger increase. Right? So how many valence electrons Na has? Valence electron, how many Na has, and how many Mg has? How many valence Na has? And Na is in which group is Na? Group 1A, so therefore 1 valence. Now, how many valence Mg has? 2. That's 2A, we have 2. Right? So that's why you remove the first electron, you are remove the valence, and that's relatively easy for the Na. So after you remove one electron from Na, if you want to remove the second electron, what kind of electron you are removing for Na for the second one? What is the second electron you are removing for Na? Core. Okay? So first one for Na is the valence, the second one is the core. So that what we said here, if you remove the core, you can remove the first core, the second core. Once you remove the first core, it becomes much difficult. Okay? If you want to compare across the period, okay? No matter you compare the period in the same period to the far right, that means it's the most difficult one. Okay? That is going to be, even though it's one on the left side, but if the one on the left side is already removed the core electron, that becomes much difficult than the one on the right that is still removing the valence. I will show you that later. But you will see here, so you see here this, the second one is higher because the second one for sodium, you are removing the core, the first core. Then the third one is also difficult, even difficult compared with the second one, because this is the second core. Got that? This is the first core, this is the valence, this is the first core electron, this is the second core. Right? Now what we are removing here, this is the first one for this Mg, what kind of electron here? This is 738. Right? The 738, so this one is remove what electron? Is this for the core or the valence? Valence. Now what about this? This is also valence. And what about this? That's the core. Right? Now that's, you can do some of those questions, okay? So once you see those successive with IE, see that we have here for those elements in our, so this is our third period, right? So last slide, we only have 12, we only have that, we only have this Na and Mg. So we use different ways to show the data. Right? We see that Na, the first one is very small number, the second one becomes much higher, about 9 times higher. Okay? The first one for Mg is a little lower, and second is higher than that. But so then the second one for the second one for the Mg, obviously it becomes harder than compared with the first one. That's the regular increases. Now, what is the dramatic large increases for Mg is number 3. By the way, there's some of those misprint from the book. Probably this is from the second edition, and you see edition 3. So I think this will be IE4, IE5. That's just very just not that important, right? So you see that the pattern continues. Okay, how many electrons the aluminum? How many valence electrons the Al has? Now you can make a list. Valence electrons. You understand? For Na is 1, for Mg is 2. Aluminum is what? 3, 4, 5, 6, 7, and 8. Right? Now you can see, you remove the first electron for Na, that's easy because you are removing that first one, or the only one valence. And so that's it. And then when you remove the second electron, we call that IE2, right? And that becomes 9 times or 10 times difficult than the first one. Okay? Now, Mg has 2 valence, so remove the first one, easy. Okay? Even though that is difficult than Na, you can use what you compare. Why that is difficult than Na? Remove the first electron, we compare with sodium. That's because Mg is to the right. Empty to the right is smaller. So in general, if you don't compare those exceptions, that is true, right? So then the second electron, the second IE, that means you remove the second electron, usually increases, even though it's about twice, so we can see that. And you can see for aluminum, 3 valence, remove the first one, and then remove this one. Even though for Mg and aluminum, you see that is the setback, so you usually will see for aluminum to the right, it's supposed to have a higher IE1, but because we have that 6th pair of irregularity, so don't be confused by that, even though AL in the same period to the right, but that are the exception we talk about those again. But you examine those 3 or 4 electrons for AL itself. So the first one, easier than the second one is easier than the third one. Then the number 4 is much difficult than the third one. Right? Why that? Because this number 4 electron you take away are not those valence, are the core electrons. Like that? Now I also tell you before, if you remove the core electron, no matter that your IE2, IE3, or IE4, then you compare that IE4 with all the other elements in the same period. If that atom you are removing is your core electron, even though that atom is on the left side, supposed to be easier because that is bigger, but because of that core electron, that becomes much difficult compared with all the atoms in the same period. That's one example, you remove the second electron from sodium. So even though sodium is on the left side, it is bigger. But because you have removed that electron, the second electron for sodium, then the core. And all the other atoms in the same period also have the IE2. So IE2 for magnesium, IE2 for aluminum. Even though the IE2 for the normal gas, is smaller than IE2 for the sodium, because you have removed the core electron. Right. So I think what we want to notice is this larger increases compare the valence electron with the core electron. And you can use these patterns and to figure out what kind of element we talk about. Before we do that, so I want to emphasize this kind of equations. Remember what I said, you should be able to write an equation for like those different IE. So this, you want to write an equation for the second ionization, which means IE what? IE2. Now IE1 or IE2, so those numbers should be on the left side because it's endothermic process. Well, I don't have that, but you, so that's probably not important. Usually you don't write that on the in the equations. So if I don't have that, you don't worry about that. You just see like what you starting from. Do you starting from the neutral atom, or you starting from 2 plus, or starting from 1 plus? That's all I have with that.
C?
See?
Answer is C. You think so?
Yes.
Okay. So then, what is A standing for?
20, or
Huh?
1 IE1.
That would be for IE1. Very good. I think the answer is C. All right. So some of those other equations, what we really not talk about in this chapter. It's possible those process, but we do not study those process. Right now, we are going to see like what you just saw in one slide, those pictures. Okay? Compare those IE1 or IE2. Okay? What do you think? Remember what I tell you? If you remove that core electron, okay, no matter where your atom, okay, and if you have the IE2, you're going to remove the core electron. Or maybe the IE3 remove the core electron. Then that IE2 will become the largest one compared with all the atoms in the same period. If your IE3, what do you say? Down to the D, right? Down to the D, very good. That's because D is potassium K, right? Potassium K is the one that has only one valence. So if you think about the second IE, which means you are remove the second electron. If you remove the second electron, and the difficult one is the one that you are removing the core electron. Right, that's good. So you think about those IE2 compared with all IE2, then you can also compare the IE1, IE2, IE3 with for the same atom. So this program has think about the regular increase and larger increase. Right? So when the larger increase happens, what do you say? Where is our larger increase? D, P. So you think about the small increase. The small increase is about to the most. If you see it twice, you still think about that the regular increase. Okay? If you see something more than three times or more, okay? That's a larger increase. And then that one that has a larger increase will be your first core. Then all the others will be your valence. So I'm just counting how many valences do you have. Right? Very good. So you have 5 regular, right? 5 regular numbers. Right? Then your number 6 become a larger increase. Okay? In this example, it's about 3 times more, right? 3 times more. That's enough. Okay? If you have 2 times more, not enough. If you have 3 times more, that's what we call a larger increase. If you have a large increase, so therefore that number has that large increase will be your first core. Before that, it be a valence. How many valences we have? 5. Okay? And then that's easy. So which atom has 5 valences? You just for those group A, you can just simply go by the group number. Right? So which one is in group 5A? The first. Got that? Right. So I hope we will have like more like these examples, but obviously you can have more examples if I just I don't give you this, right? And you can figure out what atom is what. What atom is what, right? So let's see this rule is for which group element. For which group element is this? So what I circle here? Very good. It's 6A. How do we know this is 6A? We have 6 some regular numbers, right? So now number 7, okay, number 7, yeah, so you see this is also like about 3 times more, right? Yeah. So therefore, the number 7 is the core, and then the first 6 is valence. Yeah, very good. That's about 8, right? And this is for what? This is for which group of elements? Let me just circle that in a different color. So this I circle in yellow is for which a group of elements. Group what A? You just have to find out how many group A, right? Depend on how many valence electrons. How many valence do we have? That means we will see how many regular number we have. Let's have 4, right? And so therefore this is group 1. Group 4A. You're very good. You did not like to do that. So this is group 1A, group 2A, group 3A, group 4A. You did not use those kind of techniques, but you want to understand that means you have that 4 regular number, then number 5 is larger increases. Alright, so I think that's, we're probably able to finish this chapter. So then another process is called the electron affinity. Electron affinity is about how much energy it releases. Usually it will release some energy. For some of those particular group of elements, you might also have to put an energy in to put the electron onto those atoms. I also like to talk about those gas states. Again, we use the genetic symbol for the element, which means M. M should be, can be for any element, can be for H, can be for Na, and can be for Mg. So for this electron affinity, which means you are going to put the electron onto the atom, so therefore you see the electron is at our reactants. You adding electron, if you adding electron on, you will produce a negative ion. And in this example, we don't like think about produce like 2 negative and so on. We just think about produce 1 negative. And so you will see the plus EA here. So that means those kind of process, you produce energy. So in general, there will be those exothermal process. But there are some of those atoms that may be endothermic because they are already very stable, like a normal gas. So some of those group 2A and group 8A, you might have those positive EA. So now we were like not consider this negative sign, positive sign, just see the number. Okay, if we see a larger negative number, which means we have a larger EA. Not really mathematical sense. Generally increase across a period. So that's general patterns. There's a lot of exceptions. Okay? So what we want to learn or memorize from this section. So you have this general pattern, not absolute. Okay? So now what I want you to memorize is if you want to compare those elements in the same period from left to the right, and they generally will have a more and more negative EA, but there's some exceptions. So what you want to memorize is in the same period, those halogens. You know what is a halogen? That is group 7A. Okay? So the 7A will have the most negative EA. That means they will release most energy. Okay? See the pattern here, right? So there's one exception here. Why is that? same as what we talked about before, those electron configuration. Right? So this beryllium already has that 1s2, 2s2. Right? So 1s2 and 2s2. So that becomes stable, right? If you want adding electron on, that makes it not stable. So even though the electron was, the free electron even has more energy there, but it depends on where you put them. If you capture that electron, put in a good orbital, that makes your total become less. Alright, and you can see this is true. So fluorine in this same row, right, is the most negative one, and chlorine most negative one in that one. Another pattern is about metallic caricature, characteristic. You just know metal like in the medieval diagonal. Medieval, that means you can hammer it. Diagonal, that means you can stretch it. It is usually shining and lustrous, reflect light. It has some of those very free electron moving, so therefore it's a good electrical conductor. Because electron can move, it's also a good heat conductor. And you also want to know, like most oxide is basic and ionic. So I think that is why what we did in the lab, we did a MgO. Remember that lab? And we take that with HCl, and we have an acid-base reaction. And it usually will produce the cation solutions. And actually, a lot of those metals really cannot exist as pure metals. And you can see like sodium plus. Lost electron in chemical reactions. Then briefly review what we did in chapter 4. Lost electron means oxidation, or has been oxidized. Non-metal is kind of oxidated, brittle in solid state, but not all those non-metal in solid state at room temperatures. Is dull, is electrical and thermal insulators. Most oxide is acidic and is a molecular compound. Most oxides, for example, oxide of carbon dioxide, oxide of sulfur, oxide of nitrogen. And those are the resource of the so-called acid rain. And it can produce anions. It can also produce polyatomic anions. In chemical reactions, it usually will gain electron being reduced. So you also see there's another pattern. The metallic caricature increases from right to the left, also from top to the bottom. So here is like one example about the metallic characteristic. From top to bottom, become more and more metallic. From right to the left, become more and more metallic. And this is very, very interesting. You see, like some group on the top is non-metal, then go to the bottom become metals. Similarly for those same period, chlorine is non-metal, then go to the left side, the sodium become like metals. Right, and you should be able to predicting use what we did for the. So we saw about 3 patterns: atomic radius, ionizations, then the metallic characteristic. The EA, the electron affinity, probably not that important because that's probably just as I said, you want to know like the halogen has the most negative number for EA in the same period. But pretty much like 3 patterns. I also really want to see the 4 patterns. And next chapter you're going to see another pattern about electronegativity, but then we talk about the in the bonding, in the chemical bonds. So here we talk about those patterns for the atom by themselves, or maybe the ion by themselves. Right, so choose the more metallic element from each pair. So let's say Sn and Te. Where is Sn, where is Te? So that is good Sn in this period, and then Te, so they are in the same period. So obviously the one to the left is more metallic, right? So Sn to the left, so therefore Sn is more metallic. So the other one is P and Sd. That's also easy. So P on the top, and then you have the arsenic, then you have the Sd, right? So the one at the bottom is more metallic, so therefore this is more metallic, right? So the last two, they were not in the same column, not in the same row. You have just used what we did before, right? Let's see, this Ge is here, and where is In? In is here. So Ge with guardian, and then Ge with Sn. Okay, now this is this little square of these four elements. Right? Draw arrow from here to here. Right? So both arrows tell you increasing metallic. Right? So therefore In more metallic. Right? Right? So now you compare sulfur with bromine. Sulfur and Cl and Se and Br. If I draw this way, less metallic. If I draw this way, more metallic. So one arrow tells is less, one arrow tells you more. You cannot decide. All right. So that is about this metallic characteristic. Now you do a practice. Okay? You want to put this few in the increasing order of metallic. What do you think? I think that's really increasing. Increasing. I think it's E. So let's see, you also want to know how to write down the equations. So the reaction between potassium and so those kind of review what we did in first three chapters. Between metal and non-metal produce ionic compound. Just look at what kind of ion. Right. So the first one is potassium metal with bromine gas. What kind of reaction will be this? It's kind of oxidation reaction, right? Or the combination reaction. And you will see that this is the plus one here, negative one here. Right? So the metal becomes the cation, non-metal becomes the anion. Okay, the other one is about reaction between metal and water. So some of those very active metal, like the group 1A, group 2A, you put them in water, you will see the flame and the reaction very like okay, so here is these are our metals plus water, and produce this is our base, the hydrogen gas. The last one is between two non-metals. Between two non-metals, usually will produce those covalent bond or the molecular compound. Right? Because neither of them want like lost electrons, so they will share electrons. Right. So what do you think? Right equation between the aluminum and chlorine? Yes, so this is B, right? But we know typically Al is the 3 plus. Right? So then I think the last one will be this, and this is what? This is A. I think that's it. So you turn in the scantron, right? And huh? No, Saturday. Saturday.
When's the CRE for the? Thursday?
You can